Alright everyone, today we're going to be going over section 8.3. And so 8.3 gives us two new tests. The first one is the integral test, the second one is the comparison test. So let's dive in. So the first one we're going to do is the integral test. And what this says is if you have a continuous positive and decreasing function from 1 to infinity, and you also have a sequence a sub n that matches your function f for every n. Remember, n is 1, 2, 3, and so on. So we talked about this in 8.1 with the sequences, right? If you have a sequence that matches some function, and the way that we had done this before was just replace n with x, so just as a little example for yourself. If we have this situation, then the series, the sum of all the terms of our sequence, that will be convergent if and only if the improper integral, so the series of this will converge if and only if the integral of this converges. So what this allows us to do is take a series where we look at the sequence and go, oh yeah, if that was an x, I know about this function. It lets us go back and forth between these. So we could take a series, and then what we can do is we can go and take that series and think about the function on the real numbers, so with x's, and then do that integral, and then get an idea of what should happen. Okay, so we know about improper integrals, we know how to do them, so we can use those tools. So then to break this down, what this if and only if is saying is that if the integral converges, so we do the integral, it converges, that limit exists, then the series will converge. But if on the other hand we do the integral and that integral diverges, then that means that series had to diverge. So we can tell convergence or divergence using this as long as we pick the right function. Okay, so that's it. That's the whole integral test, the entire idea. So what I did on the next couple slides, which we're going to just skip over because we don't quite have time in the semester to go through all of this, is to try to give you some intuition on this. And the basic idea, and please feel free to ask me about this, is to think of this series that we're adding, right, all of these additions, each of these terms here, 1, 1/4, 1/9, 1/16, as the area of some square. And so those squares are in blue down in the picture here. Okay, so then the idea being, what we can do is we can think about bounding. In this case, we can bound that sum of these blue areas by our integral, 1 over x squared. We can do that integral because this function, this black function here, matches my sequence 1 over n squared, right? And what we can do is we can bound the terms, these little blue boxes, by this area. And we know how to calculate this area. This area here is something we know how to do, and so we can do this calculation and then put that together to show that the series has to be smaller than that number. And since I got a number out, well, there you go, I have to converge. We don't know what it converges to, but we know there's a bound on it. And then similarly for this next one, what you can do is you can think of, again, these terms, each term as being the area of one of these blue boxes. And then what we can do is we can show that this function, 1 over square root of x, the area underneath it, which is an underestimate, that integral, this one here, will diverge, go to infinity. So if this purple shaded area goes to infinity, then that means that the blue box areas, when I add them all up, they're bigger than that, they also have to go to infinity. So that's the idea of it. Feel free to kind of dig into that a little bit. The book does this as well, so you can kind of go through it. But again, all we're going to have to do is be able to apply it. So let's just dive in. So we've got a series here, and we want to know if this converges or diverges. Okay, so we look at this, and you know, it's okay to start thinking like intuitively about this, but I know that we haven't seen too many examples, so it's a little hard to do. But what I will say just quickly for intuition, I'll say real quickly here that we know this series diverges okay, because this is harmonic. And remember, the key point in this is that the inside here, this 1 over n, goes to 0, which we need, but it does it too slowly. Okay, so then what do we think is going to happen then to this if I do natural log of n over n? Well, if I'm looking at this instead, not only do I have a harmonic, that looks something like harmonic, which is too slow, I also have this extra term on top. And as n gets big, natural log of n will get big. So that's going to slow me down even more. So this is even slower to 0, this inside term. So if I'm going even slower to 0, I've got no chance to converge. So my first guess here is that this is going to diverge. So this is my guess. Okay. Well, so what do? We look at this and say, okay, well, I could make this into a function of x's. So let's try to see if we can make this conversion. Natural log of x over x dx. Okay. So we'll skip looking at the actual conditions on the theorem just for a second and just kind of get the computation piece out of the way. So we have to do this integral, and remember that means setting up a limit as t goes to infinity from 1 to t, natural log x over x dx. And then we got to rack our brains a little bit, but hopefully we should see that it's not too bad to do a u sub here. U being natural log of x, the derivative of that is 1 over x dx. And so this becomes the limit as t goes to infinity, the integral of u du. Now again, you could either change your bounds now, or you could just switch back to x's after. I'm going to change my bounds just for practice. So when x is equal to 1, I'm going to plug that in. X equals 1, I'll plug it into my equation. U is going to be 0. When x is equal to t, x equals t, I'll plug that into my equation. U will be natural log of t. Okay, so this isn't too bad of an antiderivative to do. This is limit t goes to infinity of u squared over 2. Plug in these two. Okay, and then we're going to plug in, this is limit t goes to infinity, natural log of t, that's squared, over 2. If I plug 0 in for u, I'm going to get 0, so I can leave that. And then the question now is, let's do this limit. What happens to the natural log of t as t gets really big? That gets really big. Squaring it will only make it bigger. That's infinity. And so, since this limit is infinity, this original integral diverges. But if I use the integral test, that tells me that if my integral diverges, then this has to diverge. So this would diverge by the integral test. Okay. All right, so that is the nitty-gritty nuts and bolts of showing that integral diverges and then using it to go backwards. So we should take a moment and talk about the conditions on this, because all I did was replace x's with n's and said, okay, we're good. But let's go backwards just a second. So I need my function to be continuous, positive, and decreasing. Okay, so this function is continuous wherever it's defined, so continuity is not too bad to see. Log is continuous on its domain. 1 over x is continuous also on its domain, so we don't have to worry about anything except for these weird points at x equals 0. But x equals 0 is actually not in this integral, so I'm good. So continuous, we're good. Okay, so we needed that it was decreasing and positive. Oops. So we'll start with positive. The natural log of x is bigger than 0 when x is bigger than 1. Okay, so when x is equal to 1, this is technically 0, but if we go just a little bit further, then we're good here. So that's okay. We can have this greater than or equal to 0. And then 1 over x, that's also positive when x is greater than 0, which is definitely true because we're going from 1 to infinity. So okay, this checks out, that's fine. All right, decreasing is a little bit tougher. To show that this is decreasing, we could do a couple different things. But what we could do is we could say, well, let's define this as our function, natural log x over x. And then we could do the derivative of this. We know how to do this. This is quotient rule. So low d high minus high d low over low squared. Okay, so let's move that over here. So that's 1 minus natural log of x over x squared. Okay, so let's think about this. When x is greater than 1, right, what's going to be happening here? So I'm going to get positive, oops, not a plus 1. So I'm going to be positive down here. So I'm positive here, and then up at the top I got to think, when is this negative? Because I need to be decreasing. I want to know when this is less than 0, right? So I got to be decreasing. Okay, so then I need 1 minus natural log of x to be less than 0, which is 1 needs to be less than natural log of x, okay, which is the same thing as e being less than x. So as soon as x passes 2.71, this is decreasing. And that's good enough for me. I just need this to be true at some point forever. So at some x value or n value, I need this to be true, and then for every point after that, it needs to work. So as long as this is eventually true, we're good. Okay, so next problem. So the next thing we're going to do is introduce a really important set of series here, and this is called p-series. So for p-series, it just has the form 1 over n to the p, where n again is your variable, p is just a number. So that's it. P-series is of this form. Okay. So why am I bringing this up? Well, what we can do is we can use our integral test to figure out what should happen here. So for example, I can make the connection here to the integral 1 to infinity of 1 over x to the p. And we actually talked about this back in section 5.10. In section 5.10 we said, well, this will converge if p is bigger than 1, and it's going to diverge if our p is less than 1 or equal to. Right? So if it was 1 over x, diverge. If it was 1 over x squared, converge. This still works here now because our integral test says whatever I know about this integral, I know about the original series. So then that means for p-series, I have this fact. It will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. So let's only consider for these p-series, p is greater than 0, because if you get negative numbers up there, then you can just flip it and think about what's going to happen there. So let's stick with p greater than 0 so that our n is actually on the bottom. But that's it. That's the whole idea. You see a p-series, you pick out the p, there you go. And so this is super nice, and if you want to try to prove this to yourself, what you could do is you could just set up a couple of these. So you could do this one, you could do this integral, you could do them in Mathematica too if you want to try to help yourself. So you could do a handful of these, 1 to infinity, 1 over x to the 1/2. So do a couple of these and you'll see that it follows the rule perfectly. Converge, converge, diverge. So you'll see that happens if you do the limit, do it out. So all we need to remember is this idea that the p-series will converge for p greater than 1 and diverge for p 1 or less. So that's going to be super useful because we're going to be using that for the next test. Okay, so what is the next test? The next test is the comparison test. So how do we use the comparison test? Well, we're going to be given a series, and what we're going to want to do is figure out a series that the one we're given kind of looks like, and one that we actually know about. So the comparison test will often, we're going to compare our series to a known series. Okay, so what are our known ones? So right off the bat, we've got the harmonic. We know that one. We now know which the harmonic fits into, P series. So if we can take a series and go, well, that kind of looks like a P series, then we'll be really close to being done. We know geometric. We know how to deal with the geometric series. So right now, we've got these three types of series that if we could say, this series I got looks a lot like one of these three, then I might be able to use that fact to solve the problem. So just to kind of dig in here, it says, okay, suppose you got two series with positive terms. If B sub n is convergent and is on top of A sub n for all n, then that forces A sub n to be convergent. So what is the picture here of this? 'Cause sometimes it's easier to write this as pictures. So let's do B sub n in blue. So I'll do B sub n in blue. So B sub n maybe starts up here and then goes like this. Okay, so it's decreasing, decreasing, and we're going to say that B sub n, this sequence, when I put it into the series, converges. Okay, so then I will do A sub n in red. So B sub n is always on top of A sub n. So maybe once in a while they're the same, but it's always on top of B sub n. So what am I saying here? If I'm adding up all of these blue values forever and ever, and I converge, then that forces me to have to be able to add up all these red ones and converge, because clearly the blue sum is going to be bigger than the red sum. So the blue, when I add up all the blue values, that's going to be bigger than adding up all the red values. And that forces the red values to converge because the blue values do. Okay, same idea, just the other way for the second one. If, in this case now, your B sub n, which is the one you'll start with, your B sub n, which is the one that you'll pick to compare to, if that one diverges, right, and the A sub n is on top of that, that's going to push A sub n to diverge. So let's draw it out again. B sub n will be blue. So here's my blue. Okay. So this diverges. So when I add up all these blue dots in the series, it's going to be too big, it's going to diverge. Well, A sub n is on top of B sub n. Maybe they're equal once in a while, but it's above. So what does that mean? So if A sub n is above B sub n, and you're telling me that the series, when I add up all these blue dots, it goes to infinity, then that's going to force, when I add up all the red dots, that to go up to infinity. That's the comparison test. You look at how two series are compared, and then you look at the way one of them works, converge, diverge, and use that to get information about the other one. And again, we're going to use P series or geometric most of the time to do our comparison. So, what's the toughest part of this whole thing? It's definitely, what do I compare to? But what you need to do is be able to look at these problems and go, what matters here? So my first example is the series n equals 1 to infinity of 1 over 2 to the n plus 1. So what's the extra junk here? When I look at this problem, I say, this plus 1 here is extra junk. This is the junk. It's messing me up, right? So what do? I say, okay, well that's the junk, so what if I only considered this series? So remove the junk and see what happens. Well, we've done this a couple times. Now this is geometric, and if you do the work here, you're going to get r is equal to 1/2, which is less than 1, and converges. So make sure you can go through and do that. convergence. What am I saying here? I want to say converges. So you know that this one converges as soon as you find what R is. You're going to know this converges. So then how do we use that to show that our series converges? Well, if we think about the comparison test, what I need to have happen is I need my convergent series here. This is my B sub n, this is my A sub n. I need to show that my convergent series is bigger than my original. I need to show that this B sub n is on top of my A sub n. Because if my B sub n dots are on top of my A sub n dots, so this is A sub n, this is B sub n, and I know B sub n converges, that forces A sub n. So what do I need to show? I need to show that this is true. This is what I need to show. Right? I don't know this yet. I'm not sure if this is true. So one thing you can do when you're doing problems like this is you can kind of cheat a little bit. And why do I say cheat? Well, the way I have this set up is I've already set up what I want to show, right? I've already written that A sub n smaller than B sub n. Okay, so what you can do is you can use this. It's kind of like you're working backwards from where you want to go. You're not saying this is true, but you're going to use this and try to manipulate it until you get to something that is true, and then you can work backwards. So watch what I do here. I want to get something with just n's, because what do I know? I know that n is bigger than or equal to 1. That's what it says for both of these series. N starts at 1 and gets bigger. So I know that is a fact. So watch what happens. You could think of as cross multiplying here. 2 to the n is less than or equal to 2 to the n plus 1. So all I did was multiply across these. Or you could think of as I multiplied both sides by 2n, which canceled on the right, put it on the left, and both sides by 2n plus 1, canceled on the left, put it on the right. Okay, so I've got this is true. All right, now I could keep simplifying. Well, I can subtract a 2n from both sides. So let me not write it like that for just a sec. I could take a 2n away from both sides. And that gives me 0 is less than or equal to 1. Is this true or false? This is true. And so what you could do is you could work your way backwards. So watch the way that I do this if I go backwards. So I'll be okay if you stop at this point, tell me true, because we can just run everything backwards, but I just want to show you what it looks like. So okay, I'm going to start with a true statement here, and then watch what I'm going to do. I'm going to add 2 to the n to both sides. Okay, so that's 2 to the n is less than or equal to 1 plus 2 to the n. Okay, now what I'm going to do is I'm going to divide both sides by 2 to the n and both sides by 1 plus 2 to the n. So that'll give me this. And hey, look, this is exactly what I had wanted to show to start. So I just literally ran every single step I took on the left. I did it on the right. I just reversed what I did. I reversed the order. I went backwards. Okay, so we know then that that's true. We know then that B sub n is always bigger than A sub n. So what do? So the comparison test tells us that since B sub n is bigger than A sub n and B sub n converges, then A sub n converges. Or, sorry, if the series B sub n converges, then the series sum 1 over 2 to the n plus 1 converges. So that's our conclusion. We used the comparison test. We saw that we found a B sub n that was bigger than our original terms. B sub n 1 over 2n, well, that was bigger than the original. And we saw that that series converged. So that pushes down my series, forces it to converge. And that's the idea. So let's try another one. So okay, I'm looking at this one, and again, it's all about trying to see through what's happening here. So what do I mean by that? Well, what's the extra junk here? So to me, again, I see this +1 is the junk. Okay, so why don't we just remove the junk and see what happens? So if I remove the junk, I'm going to get this. But I can simplify that to this. Okay, and what I see here is, hey look, I've got a p series. So this 1/2 can be moved out, and I literally have a p series. So this is p series. P is 2, okay, which is greater than 1, so convergent. Because I just say p series, I know what p is, it's bigger than 1, convergent. Okay, so I have got a series here that is convergent. So what do I need to do? I need to show that my new series is bigger than my previous one. So I need to show that my new series that I had just figured out, which was 1/2n², I need to show that that's bigger than my original one, right? Because if it is, I can use the comparison test and the fact that my new series is convergent to show my old series, this is the old one, is also convergent. So again, what I'm going to do is I'm just going to work my way kind of backwards, trying to get to n. So I'm going to multiply both sides by the denominators. So I multiply this way, that gives me 2n³. I multiply that way, and that gives me 2n³ plus 1. Okay, I subtract away these 2n³ because they're similar on both sides, and I get 0 is less than or equal to 1, which is true. Hooray! So in this case, I could walk my way backwards, starting at this line and going back up to my original inequality. But if you get to this point, that's fine. You don't have to work your way backwards. So then this work shows us that our original sequence here, n/2n³ plus 1, is always going to be less than or equal to our new one, 1/2, 1/n². And I know my new one's bigger, so by the comparison test, since my new sequence is bigger than or equal to my old one, and my new series from 1 to infinity converges. So remember, this is our b sub n here, this series of b sub n. Since that converges, then my original must also converge. And we got it. Boom. So there you go. Alright, let's try one more. Okay, so again, you got to be looking at this, trying to think, what do I see here? What do I see here? And if you're having trouble seeing it, just throw out the junk. So in this case, this to me looks like junk. Okay, so let's throw out the junk, see what we get. This n equals 1 to infinity of 3 to the n over 2 to the n. Okay, so hopefully you're seeing some geometric in here. And if you don't see it yet, remember you can combine those into 3 over 2 to the n, which if we want it perfectly geometric would be 3/2 to the n minus 1. So look, I'm geometric. My r is 3/2, which is bigger than 1. And once I get an r that's bigger than 1, this diverges. Okay, so I found a new series, right, that looked a lot like my original, and this one diverged. So what do I need to do? I need to show, so remember, this is my a sub n to start, this is my b sub n. Okay, so what do I need to do? I need to show here that my new one, b sub n, is now smaller than my original. So that's the same thing as saying this is smaller than my original. That's what I want to show. I need this. Because if I can show that this is true, then I can use the fact that my new series diverges to show that it's going to force my old one to diverge. So again, I just try to kind of work my magic here. I can cancel these on both sides. Oh, I can cancel these on both sides, and I get this. True. This is a true statement. Excellent. So again, what you could do is you could work your way backwards, starting from this statement all the way to the top. But this is a fine amount of work. You got to a true statement, so okay. So what does that do? That shows you that your new sequence is less than your old one. Okay, so if I get a new sequence, then that's less. Remember the way this works. Here's my B sub n. Oh, let's start it a little bit higher, actually. So here's my B sub n going down. Okay. Well, my A sub n, so B sub n's here, my A sub n is above it, right? So this is what this is saying. My A sub n is above it. Okay. Well, why is that helpful? I know that the series the series B sub n diverges. So when I add up all of these values, all these dots forever and ever, that sum is too big. It's too big. It's big, 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 going to go to infinity. But A sub n, look, the dots are bigger. That means that that sum is also going to get too big, too big, too big. So by the comparison test, since we just showed the sum of B sub n diverges, and we showed that our B sub n is smaller than our original A sub n, then this series also diverges. And we're done.